for our next test, I think my arrangement is for our second test will be covered up to chapter 6. And right now we are in chapter 5, and one more chapter, chapter 6. And then once we complete chapter 6, complete the homework exercise for this and for chapter 6, and then we will go to prepare the next test. Okay, so from here, the remaining topics here is in chapter 5 is a higher order systems. So right now you can see for chapter 5 we have introduced the first order system and second order systems. And we spent about 2 lecture hours on this kind of topic, in particular on the second order system, because that is more, has provided some more dynamic information. And in the beginning of this chapter, I said the first order and second order system are approximated systems from the real one. And most of the real systems are more than the higher degrees. So here we a little bit talk about the higher order systems, and then we see how can we do about this one. So general, for example, this is one example of the block diagram, and GS and HS can be whatever the content is. And the transfer function for this example will be look like this, okay, in terms of the G. And for whatever the content, if say we put a very general, say the G equal to this, and multiplication of 1 plus GH could be like this. Okay, here is we put into symbolic the representation. That can be a very, very general description of the transfer functions. And here you can see the degrees in denominator is n, and here numerator is m. And usually the m is less than n. That is for the most of the case. So from here you can see this one here, we don't say n equal to 2 or n equal to 1. So here we say this in general, this representing is the higher order systems, okay? And so for whatever the higher order systems, I believe, right now if I say, please calculate the response of C in, to unit step input, to unit ramp input for this system, are you able to do it? Yes, say you can use MATLAB, right?
Yeah.
You can use MATLAB and quickly, and if say don't put it into the chat, I give you enough of time, you should be able to give a very good analytical result for such a system. And that is the thing. Okay, so at the end of the semester or in the future, say if you go out to work, are you able to do this kind of things? Yes, you should say yes. Okay. And without any hesitation, I can do it, okay? And now the matter is whether my answer is correct or not. Just say yes, okay. Okay, so that is the general concept here. And in principle, actually, everyone can calculate something at this moment. And if you really want to do the calculation analytically, you know you can, just like we did before, you can factorize the response of the output to whatever, and then you can factorize and then try to use inverse Laplace transform. Okay, and that is the step here. And this page is not that important, but the figures here. And here I want to show you is this. So if you're able to do the analytical calculations, then you should be able to find the poles of the system. And for second order system, we have 2 poles. For 3 order system, we have 3 poles. For n order system, we should have n. The number of poles should be equal to n. Okay. What is poles? What are poles? Poles means the roots of the characteristic equations. So we're back to this page. So poles representing is we're simply setting up the denominators equal to 0. We solve this characteristic equation, and the roots are the poles of the system. So for n order system, we should have n poles. Okay, and so in addition to solve for the response of this system to, for example, unit step, and by MATLAB, you can see you should be able to see the curves. And before doing that, you might be able to locate the poles of the systems And before you go to the detailed analytical solution, you might be able to, from the location of the poles, you should be able to tell how or what the system would look like. Okay, so that is before you spend your time, couple hours, you might be quickly locate the location of the poles, and you can tell the system's behavior. And here, in this way, assuming we have the number of n, the number of the n poles here, and then we can identify what we call the dominant poles. And here is a key terminologies here. And here, for the first time, I introduce you the dominant poles. The location, the dominant poles are the poles which dominate the characteristic of the dynamics. How to say that one? So again, this is the complex domain. And for example, let me introduce you the concept of the dominant poles. For example, here we have two poles here. And say one is s at equal -1, the other one is s, for example, at -100. I make a very exaggerated examples here. So we have two poles. This is a second order system. And for the second order system, say S1 equal to -1, S2 equal to -100. And those are the poles, and basically solving for AS plus B equal to 0, then we have the solution, right? So we kind of backwards right now. I kind of give you again, here I'll try to give you certain feelings about what means the dominant. So if we have this one, then we can re-establish what is the corresponding characteristic, and this actually is corresponding to 11s plus, 101 as plus 101, right?
No, plus 100.
S plus 1, S plus 100.
Yeah.
Yes, S squared plus 101, S plus 100 equal to 0. Okay. So basically for this one, what system will look like this? The system will be looking like this is S squared plus 101, S plus 100, and multiply with certain state. I just actually make one number here, so that is our transfer functions. Okay. And this transfer function, if you're going to do the unit step input, and say you can calculate, say, if the C over R equal to this one. So you might be able to calculate the response to the unit step input, and then you can set R equal to 1 over S, etc. Then you can solve for, okay, then eventually, a few minutes later on, you can see the output will be dominant, will be governed by the two terms, exponents T plus exponents 100T. Whatever the AB is depends on the conditions. But eventually the system will be governed by the two exponents terms. Okay? And really doesn't matter that is in response to unit step input or to unit ramp input or to unit the impulse, then the two terms, you see the two terms will appear. The coefficient just be tuned in response to different inputs. Okay. So from here you can see the output is governed by the two modes, and this mode is very slow. Let me draw here, this is time. And this is the exponent of minus t. The other one, this is exponent minus 100t. So here the solutions, the output is these compositions of the certain modulated combination of the two curves. Basically you can see this response, this dynamic feature basically will be governed by this one. Right? This is the slow, this is a slow one, this is a fastest one, right? This one corresponding to this mode here. Okay, so here the whole story, the demonstration to tell you is this. Because the location of this pole is the closest to the origin. it represents the slowest mode in the time domain. So in the time domain, we say the dynamics is governed by this one because the dynamics is mainly is features by the slowest mode. It provides the most significant. It dominates. Basically, I would say this mode dominates the behavior of the output. So here, corresponding the pole, we call it's called a dominant pole. Here we only have one dominant pole for these illustrations. And for other illustrations, for example, here we have the different systems. Say this is again in the real domain and in the complex domain. So if we have, say, the complex conjugate poles here, and for example, here the location is -1, and then we might have, say, here, for example, -10, and then, for example, here we might have another complex conjugate, say, at 15. So compared to this one, you can see the two poles basically closest to the origin, to the imaginary part. So we can tell the corresponding time domain response will be governed, will be dominated by corresponding the decaying mode of the two poles. So here we call this called the dominant poles. Okay, the poles which will dominate the time domain response of the system. Okay, so put everything in a single word. The dominant poles are the poles closest to the either to the origin or close to the imaginary axis. One word. Okay. And so that is the first one. The second one, here we have known the stable and unstable. So we know for if the poles has a negative real part, then we know that's going corresponding is the exponential decay. If we have poles corresponding to have the positive real part, then we know that corresponding is the exponentially growing. So here for the positive real part, we call it unstable. Okay, and this is called stable. And next chapter 6, we're going to talk about the instability. So which means we're going to talk about a stable or unstable situation. And again, if we only have the poles on the real axis, we know the response is like this. Poles have the imaginary part, we know they're going to oscillate. So that is the trivial things. Okay. Yes.
What if the pole in the unstable region is closer to the imaginary axis, and the one in the stable region? Is it still more dominant? So
You say if the poles have the one is here, one is here.
No, if you have that system, but pole
We
one
have the
is
system like this. Okay.
Yeah. Is the system just completely unstable with
Yes.
that pole dominating?
As long as we have one pole, in the right hand side, then the system is unstable. As long as there's a one, doesn't matter how many, at least one, then the system will be unstable.
So it doesn't matter that the stable's closer to the origin.
Doesn't matter. Doesn't matter. Yeah, because you can feel because for each term, eventually the output will be superposed of every single mode. So as long as one is there, then that will make the things unstable. Okay. Okay, and now I want to talk about is under certain situations we might be able to approximate the higher order systems by lower order systems. Okay. So here we talk about is again the dominant poles and again I have included the dominant poles here. So basically the dominant poles basically are the poles that closest to the imaginary in the vertical axis or the origin here. Under certain situations, we might be able to ignore the influence of those we call the insignificant poles. Using this example here, you can see this one, this decays so much, so quickly. So basically, after the certain period of time, the contribution of this fast decaying behavior will be gone. The whole system will pretty much will be, if we say the system will be approximated by this one only, it's good. Good enough. If say after a certain time, the period of time. Okay? So from here you can see, using this as one example, basically the difference is the gap is 100. Basically is 100 times of this distance. So here we are able to approximate this second order systems by simply the first order system. Okay, so here a kind of schematic introductions is this: if in certain situations or in certain applications, if at the first step you locate all the locations of you locate all the poles on the complex plane. At the first step. The second step, you simply observe if you be finding the clusters of the poles into, say, the group like this, and there's a clear gap in between. Okay, the size of the gap basically is taken as at least 10 times of this distance. You simply identify what is the cluster range, and here you multiply with 10 times. If they separate by 10 times of this one, you pretty much for sure you are able to ignore the influence of this. Then you can approximate the higher order system by simply looking at the response here. Okay, so here for the keyword is this one, the gap is 10 times of whatever the region here, the size, the dimension here. Okay, so for example, if we have the system so if we have the poles here and this is -1, and say here we have another pose here, if say this is -12. So from here, this one you can see the gap here is 12 times of this distance. So basically this size here is won't give us very big the contributions to the output. Okay. So this is the original is 1, 2, 3, 4, 4 poles is a fourth order system. And should be able to be approximated by a second order system. Okay, and how to make a good approximation? The brutal way is you just directly eliminate the two poles, and then writing up the corresponding equation for the two poles here. And the next section we will provide a better approximation to approximate the higher order system by the lower order system. Okay, so here is the concept. So we go to the next page. Okay, and I think this is another kind of side discussion. Right now I'm designing the homework 4, and one question is this. This slide is kind of side discussion, nothing related to any topic. And for example, say if I say I wish that I can build up the system, the second order system have the maximum the maximum peak, say less than 20%. I wish the peak time, the time to reach the peak is say 1 second. So from the two situations, I should be able to find the data is less than or equal to certain numbers, and omega n should be greater than or equal to certain numbers. And I ask you, give me the range of the legible selections in the complex planes corresponding to this one. And let me show you. For example, here, so say if this is less than 0.1, so if this is greater than 10, what would be the range in the complex plane? So we can try is this. We know the omega n is governed by a circle. So here is say 10 equal to omega n. So all the areas outside of this circle will be eligible for our selections. Okay, then the second one, so we fix this. Then the second one is this one. So what is zeta? We know the angle. This is a cosine zeta, right? So you simply calculate a cosine of 0.1, and that one is how much? Uh, 0.707 is 45 degrees, and 0.01, I would guess this is 6 degrees, whatever. Okay, I just make it up, okay? So here is the 6 degrees. So this one is less than 6 degrees, so that means we have the angle is greater than 6 degrees, smaller than this degree. So in this way, here the intersected regions, basically here this kind of sector region from here outside, that would be the region able to allow us to pick. That be okay? So one homework question basically is like this. And based upon the range of each parameter, we are able to select something from here. And once we identify the target region, then you basically, for example, for the second order system, you simply can locate your poles there, and from there you can do something. Okay.
Your omega n says greater than 10, so shouldn't it be everything outside of 10?
Yeah, everything outside of 10. So everything outside. Yeah.
Okay.
Okay. Refer to our textbook and the one section in chapter 5. Basically, here have this kind of things. But if you know the concept, you should be ready quickly. Okay. The next one. Here we're back to the approximation of the higher order system.